Good morning and a warm welcome to this session on geospatial design analysis. My name is Ian Slingsby and we have four excellent talks for you today, broadly on the subject of designing visualization for geographic data. Please do ask questions during the talk in Discord and YouTube chat, and I will try and put those to the presenters who will be answering questions live after each of their talks. So let's move on to the first talk now. The first talk is about a deeper understanding of visualization text interplay in geographic data-driven stories by Shahid, Latif, Chen, and Fabian Beck. It'll be presented by Shahid.
Hello and welcome to our talk. I am Shahid Latif, a PhD candidate at University of Duisburg-Essen, Germany. Today, I'm going to present the findings of our qualitative analysis on a set of professional data stories with an objective to derive guidelines or best practices that can be helpful in an effective story design. This work is done in collaboration with Chen and Fabian Beck. Text and visualizations are two integral parts of a data story. Both play different roles in a story. While visualizations show the underlying data and allow for exploration in many cases, textual elements provide explanations and incorporate context behind the data. Stories can have different forms. Some are visually dominant and include few textual elements. These elements can appear at various places in the story. Others may include longer textual explanations which may serve various purposes in the story. These explanations can provide backdrop of the story, explain how the data was collected or prepared, or explain analysis insights. As intrigued visualization researchers, we were interested to know what makes these stories effective, and what factors should be considered to design such stories. Taking into the existing literature provided us with some answers. Different design strategies, structuring, and sequencing, as well as the factors that influence the reading experience, are all important. The design space analysis of professionally written stories is a great way of revealing important design considerations as demonstrated by these papers. However, the role of textual narrative is somewhat underexplored. We believe that investigating the purpose of every sentence and visualization within a story and how they reference each other can further shed light on achieving a more coherent representation in these stories. We refer to our analysis as the fine-grained interplay of text and visualization. For investigating this fine-grained interplay, we came up with two main research questions. The first question relates to individual ingredients of a story, that are text and visualization. The goal is to look at the narrative to find out what the prominent insights are, how context is blended with them, and how these insights are communicated, both textually and visually. The second question, on the other hand, focuses on the interplay. In particular, we look for what type of links exist between the two media and how they are co-referenced. Also, we were interested to know how and in what sequence are the visualizations embedded into the narrative. As for the analysis, we restricted ourselves to stories that talk about geographic data analysis and include at least one or more geographic visualizations. The main reason for this was the spatio-temporal nature of data, that what we believe makes the data reporting more challenging. Besides, it usually requires versatile visualizations to show different aspects of such data. For instance, some visualization with a geographic focus and others with a temporal one. We analyzed 22 stories, which were collected from 10 well-known journalistic sources, with majority of stories coming from three sources: New York Times, 538, and BBC. 12 of the stories were collected on a variety of themes such as culture, economics, politics, science, and health to maximize the diversity of topics. The remaining 10 stories were on a single topic of COVID-19. These stories have the same context, yet they cover various aspects of the pandemic. We divided every story into individual sentences and visualizations. This resulted in almost 1,200 sentences and 118 visualizations for all stories in our sample collection. The open coding of all the sentences and visualizations resulted in 45 distinct descriptive codes. These codes are organized into 4 categories and 12 subcategories. The textual narrative is roughly split into 2 parts. First, the data-driven part that communicates the analysis findings. This part of the text implicitly references various parts of the visualizations. Second part of the text serves as an embedding and either provides structure to the story or adds various types of context. The visualization text linking category refers to either the text elements that appear inside a visualization or those sentences in the textual narrative that explicitly refer to the visualizations. Here is an overview of all the descriptive codes along with their frequencies of occurrences. The structure of sentences is usually complex and sometimes not possible to split them into disjoint and non-overlapping codes. Therefore, we allowed multiple assignments to a single sentence. Same was the case with visualizations. Let's look at different code categories a bit more closely and try to answer the first research question. While it was no surprise that location and time were described very frequently as we focused on geographic narratives, we see that insights closely relate to high-level analysis tasks. They can be grouped into identify, summarize, or compare tasks. For instance, identifying data points that are unique and then describing them individually or as a cluster. Here you see an example of an outlier with respect to both geographic and temporal variables. It describes that California had the highest number of public mass shootings to date. Here is another data-driven sentence that describes statistical relationship between 3 variables. In the perspective of French presidential elections, it describes that areas with high median income were more likely to vote for the centrist candidate. But the effect was not the same when education was taken into account. Sufficient background or domain-specific terminology that is needed to understand the story is included. Here is an example sentence that conveys domain knowledge about inaudible noise in a very simple language. We also observe specific descriptions about the dataset that can make the analysis more transparent. For example, explaining as to why some parts of data were filtered out. Similarly, authors of the story interpret the insights, deduce other insights, connect insights with quotations from researchers or policymakers, and even add their personal judgments. As for the visual communication of insights, we observed the use of 8 different types of visualizations in our sample collection. To classify all visualizations into distinct types, we used the visualization taxonomy as used in the work of Porkin and others. We also tried to determine the purpose of every visualization in the story. We observed that visualizations mostly serve 3 main purposes. They can provide an overview, facilitate comparison, or highlight details with respect to a certain aspect. These purposes are overlapping, and a single visualization can serve multiple purposes. Map visualizations were most frequent, and they were a standard and common way of providing an overview of the geographic data. Among maps, the choropleth maps were more common. Going beyond just the geographical variable, animating a map was a way of providing geo-temporal overview. However, maps were mostly limited to a single statistical variable. Extending maps beyond a single variable and to allow comparisons across 2 or more variables, multiple versions of a similar map can be placed side by side. Small multiples are yet another way of providing temporal comparisons of a variable across many different regions. For example, every country or city can have its own line or area plot on a similar scale. The use of tabular visualizations was also frequent. Unlike choropleth maps, tables are very flexible and can even include uncertainty or distribution of the variable to allow even better comparisons. All tables in our sample collection used some type of visual encoding or sparklines embedded in them. While most of the visualizations were quite standard and well known in our sample, We also observe the use of some less well-known visualizations. For instance, the use of colored overlapping semicircles in a timeline to provide an overview of two variables or a bee-swarm distribution plot. Now that we know about the ingredients of the stories, let's look at the structure and how they interplay. Here we see the structure of all stories in our collection. Every story is represented with a series of colored rectangles. The color represents the code category. The width of each rectangle corresponds to the length of the sentence in words. To get a comparable scale across text and visualizations, we approximated visualization as to the number of words that would fit in the same screen space. We found that highly explorable stories tend to be shorter. For instance, A1, A6, A12, B2. One of them even includes multiple visualizations linked via brushing and linking. We see that stories are structured in different sections. Black rectangles mark the beginning of a new section. Almost half of the stories begin with a visualization that in most cases is an overview visualization. Comparison and detailed visualizations usually appear after the overview visualization in the later section of stories. Schneiderman's visual information seeking mantra, overview first, seems to apply here as well. The data-driven text, that is green rectangles, tend to appear closer to their related visualizations. Although this fact is hard to confirm from this figure, as it does not take into account the layout of stories, which greatly affect the positioning of the text. We observe that majority of visualizations in our sample collection add textual elements in them. Examples of these are captions, titles, annotations, and tooltips. It was interesting to note that less well-known visualizations tended to have longer captions and more textual annotations. This distribution plot, for instance, has a title, subtitle, and a textual annotation that describes the main takeaway from this visual. In some cases, textual annotations inside a visualization may explain every part of the visualization. Textual elements inside a visualization not only makes it a self-sufficient unit of information but also serve as anchor points that are picked up in the text and makes it easier for the reader to quickly go to the relevant part of the visualization while reading the story. The visualizations are placed close to the text that describes them. This way, they can be easily referenced and do not require any numbering. In some cases, visualizations are introduced before their interpretation. This usually includes the explanation of visual encoding or specific aspects of visual design that may have influenced the data representation. Finally, the use of consistent colors to format phrases and the textual narrative according to the visualization is another type of linking we observed in some stories. This type of linking can enable quick reading as users can quickly and easily find connections of various parts of visualization in the textual narrative. Grounded in the analysis, we came up with 9 different guidelines, or we call them best practices, that we believe can be helpful for the designers of similar stories. While the complete list can be found in the paper, I will describe a few of them here. The first is to provide sufficient background information. Since the target audience is broad and diverse for such stories, it is important to include domain-specific terminology in the story so that the readers can easily follow. Second is the use of vernacular or everyday language to describe domain-specific terms or geographical entities. It is also important to describe what is visualized and how it is visualized. For instance, explaining non-intuitive visual encodings, especially if the visualization might not be familiar for every reader. The visualization placed next to the text helps the reader better understand the description. It avoids unnecessary scrolling or other similar interactions for connecting the visual with text. Finally, the addition of textual elements can make the visualization self-explanatory, intuitive, and can hint at specific insights. Expressive annotations even make it possible to use non-standard and less well-known visualization in a story. With our analysis, we took a slightly different perspective and tried to understand the role of textual narrative in more depth. We hope that the identified best practices will help authors of data stories. We also hope that they can be valuable in informing the design of visual data reporting solutions or story authoring tools. We believe that the identified qualitative codes are a valuable contribution and can be easily extended to other types of stories. That concludes my talk. Thank you for your attention, and I'm happy to answer your questions.
Okay, thank you, Shahid, for a very clear presentation. So we have Shahid here for questions, and we have a few questions already. Thank you for that. So there's a question from Helvik Hauser, who's asking whether these stories, well, he would assume that they're not independent over time, that authors are likely to adapt and produce stories that converge to successful formulae over time. And also, I was also thinking that you had 22 samples of stories, many from the same publication, who probably have the same style. So I wondered if you could comment on that, whether you saw evidence that successful formulae were followed over and over again.
Okay, yeah, that's a great question. Yeah, so we observed that the stories were not like from one time, but it was like a succession of events from the past. So this was reflected from some of the categories we have in the paper as like quotes. So they were like indirect quotes and quotes where they were quoting some policymakers and so on. But yeah, also I think one of the examples in the outlier, like about the California shooting, it was also taking the time into perspective that it has had more shootings than any other state. But we do not specifically consider this aspect, but it was pretty much evident into the sentences. But I think the only quotes we have along those lines were quotations, direct and indirect.
Okay, thank you.
Yeah, with respect to the second part of the question, Aidan, so there was, of course, so I think the New York Times and especially the 538, they have this tradition of having one story and then they usually post updates onto these stories, how the situation evolves. For example, the results of an election or, for example, the pandemic situation and so on. But we kind of restricted ourselves to just one version of the story. So we did not follow up on the stories, how the situation is evolving, but we just took the stories from one point in time and then analyzed those.
Okay, thank you very much. So there's a follow-up question by Till Nagel, who's asked whether potential public data literacy increases due to the pandemic and all the visualizations that have been produced there has had an influence. And I guess it also relates to the last question because many of your visualizations were about the pandemic. And I wondered whether there was whether the style converged because so many outlets were producing that.
Okay. Yeah, that's a great thought. So we don't really have the evidence in terms of how the literacy can increase with this, but we kind of, while analyzing the stories in the first collection, which was diverse compared to the other one, which was more onto a single topic, we realized that, for example, the visualization introduction part or introducing the data part, or sometimes the authors tend to include the domain knowledge inside the story. But in the stories that were related to the pandemic, we observed less sentences compared to those. So it was due to, of course, the fact that they use more straightforward visualizations for reporting the pandemic. But of course, there were different perspectives of the pandemic. So I think there were quite some complex visualization in that regard. But as was mentioned before, the use of textual annotations or explaining every part or every line into the visualization, that I think definitely can help increase the visual literacy of common people. So they don't have to wonder what this line means, because then there is a descriptive caption or like a tagline which clearly says, okay, this is the main takeaway from this visual.
Okay, thank you very much. So there's a good question here from Wolfgang Eigner, who's asked whether you looked at interactive elements. So did you have text and visualizations that simultaneously highlighted? And also I wondered whether you had any narratives that encouraged the viewer to think, or were they all kind of quite passive? They were trying to present stories in a passive way?
Okay, so we also observed, so I think in more than like in 3 or 4 stories, there were of course this interactive linking between the text and the visual elements. For example, there was a sentence and there was a visual, so there was a consistent color used to explain the same concepts. Like some keywords were highlighted in the text using a background color, and if the user hovers over those, the related part of the visual kind of gets highlighted to so this way it enables actually so that you can explore the story first and then read the corresponding text. So you don't have to read the story passively. Of course, there were some stories which were highly explorable and interactive. So there was not much narrative in those, but of course it was how the data was visualized and the user was kind of free to explore those. And there was follow-up linked visualization that explains different aspects of what you can explore in those. So yes, there were these exploration kind of stories which kind of helps people think into certain directions, which invoke or provoke this kind of thought process into the users. But I would say that most of the stories were kind of passive, telling a story in a very interactive way, still in an interactive way, even though without, let's say, explicit interactions.
Okay, thank you. There's a question here from Jason Dykes, who's asking, he says that one of your guidelines was that is sufficient background sufficient? So what is sufficient in terms of the public, and did you see differences in the audience types between the different outlets that you looked at?
Okay, so yeah, so I think this is kind of hard to define what sufficient would be, because then it would highly depend on the previous knowledge of the audience who is reading or interacting with the stories. But we kind of assume that the stories are for general public, so everybody should be able to understand those. So for example, if you are trying to use some kind of terminology, in one of the stories, it was about the loudest place on Earth, and it was all about the seismic waves, which do not produce any sound. So in that case, the authors kind of included the definition of seismic waves or how this infrasonics work and so on, so that the user is at least at one point where he can actually understand what this noise is about.
Okay, thank you. And now there's a question from Michael Kramer, who's asked, who says it's a very nice talk, and he's also asking what your future plans are. So I wondered whether you were perhaps thinking of looking to look at more examples to see whether your design space completely covers them, for example, or perhaps setting up some enhanced guidelines for people. So what plans do you have?
First of all, thank you for the compliment. Yeah, so we do have some plans. So we were also kind of, apart from this having the best practices we highlighted in there, we were moving in the direction of where we can actually think about automatically or semi-automatically generate the narrative itself. We also have one section kind of towards the end of the paper. I would recommend everybody who is interested in reading that. So that is also one plan to how we can actually automate the process. We already kind of explain a few things in there, what parts of the narrative, especially the data-driven part of the narrative that I was talking about, like outliers, extrema, summaries. These things might be easier to automate, but the other part that is kind of very well connected into the narrative, that might be a little bit harder to generate, or even kind of impossible actually to generate. But yeah, that's also one potential direction we are looking at. The other one would also be, for this one, I think we just use one metric for mapping this the space visualization take in a figure or in a story compared to the text. So we just use one metric in there without considering the guidelines, because every publishing agency has their own guidelines into what font sizes there should be, how much should be the size of so these things could also be considered. I think that would also be one interesting direction to follow.
Okay, so there's a suggestion from Jason that maybe you could look at different audience types. That could be something to look at in the future. Quickly, a question from Kunting, who's asked whether there were similarities and differences between this approach and that of, say, data comics, or even academic academic papers. Did the narrative structures differ?
Yeah, first of all, thanks Tyson for the suggestion. Yeah, so I think there was clear differences. I didn't look at the data comics in much, I think, in more detail, but I think I can compare to the scientific papers. So in scientific papers, usually the visualizations are included, and the kind of the captions are mostly explain, especially in the visualization community, we have the captions that are explaining different type of encodings and so on. But I think in these stories, the captions are more like what are the main takeaways, what is the main message from the visual, and they use much more textual annotations on top of the figures in these stories. Also, there was no cross-referencing we observed, so there was none actually. So in papers, we always refer to the papers. Okay, look at figure this and that, but in these, I think the placement of the visualization is quite important, and they're always placed right next to the text that is describing. This also kind of aligns the narrative into one screen because they are like scroll down stories. So it helps in, I think, better maybe reduce the cognitive burden on the user, so users can, so they don't have to kind of explicitly reference various part of the figures. So also maybe one main difference I would highlight here is kind of the use of text inside the visualizations. So that we observed much more, I think, if I'm not wrong, compared to the scientific publications we have.
Okay, thank you. And thank you everybody for your questions for Shahid, and thank you for answering them so well. So let's thank the speaker, please.
Thank you so much for having me.
Okay, we're going to go to our second talk now. Our second talk is about a design space of origin destination data visualization by Martijn Tennekes and Chen. So I'm looking forward to this because it's a topic quite close to my heart, and this presentation will be presented by Martijn.
Everyone to my presentation. My name is Martijn, and it's a joint work with Chen from the University of Oxford. I'll talk about the design space of origin destination data visualization. First of all, origin destination data describes flows between origin and destination. Main examples include human mobility. Other examples include transport of goods and pandemic spread. We'll focus on commuting. By administrative data sources, we know in the Netherlands where people work or where they live. So this allows us to create this map. This is a standard flow map where curvature indicates go to work. This map suffers a lot from cluttering. We can solve this by applying some basic filtering and color coding, as shown here. This gives some improvements. However, cluttering is still not solved. Therefore, we have found a new way by using a design space. And this talk is about the design space. So this donut map is actually a result of this, applying this design space. So this donut map shows half lines instead of whole lines. The lines are drawn from midway point to the destinations. The donuts themselves indicate where people commute to. So each donut, so for instance the pink donut, it shows where the residents of Amsterdam go to. So this is the interactive donut map. The lines have been colored by place of work. So all the red edges indicate people who commute to Amsterdam. The green ones, people commute to Utrecht, purple commute to Rotterdam, and orange commute to The Hague. By showing the half lines, it's quite easy to compare the flows. So you can compare the flows between Utrecht and Amsterdam by just comparing the width of these edges. The donuts themselves, they represent where people work. So the majority of people who live in Amsterdam also work in Amsterdam. And you see that in the surrounding areas, surrounding municipalities, for instance, how many people work in Amsterdam. So there's still a pink color. So policymakers have found this specific visualization method quite useful. We still cannot guarantee whether this method is also useful in other applications. So that's one of the reasons that we introduced the design space, because you want to explore all the options that are available and create the best visualization for the specific task at hand, for the specific target user, etc. So this method, so clustering, is further reduced, and user tests are recommended, of course. In this talk, I'll show how we came up with this method and what other benefits there are by having a design space. So the design space is needed because there are many origin destination data visualizations methods like these ones, already starting in the 19th century by Minard. Each of these methods uses specific ways to lose information. Information loss can be obtained by node aggregation, edge bundling, and so on. And design space maps out different ways to lose information. It's kind of a systematic way to lose information. It's also possible to bring back information if necessary, for instance via interaction. We applied a narrow definition of a design space, which only focuses on a visual representation. Other studies that have introduced a design space for other domains often used a taxonomy or ontology. However, those are often based on additional parameters, such as data variations, users, and tasks. Often they are constructed using a divide and conquer approach, and moreover it's not easy to identify new design options. However, in the way that we have defined our design space, it's quite easy to identify new design options. So when we plot the visual designs as dots on the left-hand side, we can use these parallel coordinates to see what options there are. So in this case, we have 4 dimensions. So each dimension represents a specific area in which to lose information. So dimensions 1 and 2, they represent the data structure. So basically we have an underlying graph structure with nodes and edges. D1 is for the set of nodes, D2 for the set of edges. Dimension 3 and 4 are used for the visual attributes, for the visual variables. D3 is for each of the nodes and dimension 4 for each of the edges. When we start with the first dimensions, so the first dimension is a transformation of a node set. We consider 4 basic types of operations. A filter, which can just filter nodes, for instance, based on a bounding box or based on an attribute value. A group is like an aggregation. You can aggregate nodes by a grid cell, or by administrative area, by cluster, or by same coordinates. Other options are to add nodes and to split nodes. So the add and split are basically operations that reintroduce information. When we apply this to examples from literature, we see the following. If we take OD maps, so an OD map is, in this case, a map of the United States. Each of the rectangles represents a certain area. It represents the origin of this area, and it shows a small map of the USA, which is kind of a heat map that shows the destinations. So if we apply dimension 1, we see that the nodes have been grouped by grid cell. If we look at another example, the spiral trees, then the nodes have been aggregated by administrative area, in this case, state. A third example, the mobility graphs, they have two preceding steps. In the first step, flows are filtered. It's filtered based on the attribute value of the nodes and the edges, but I'll come back to that later. It's also in the next step, the nodes are grouped by cluster. So nodes that are in proximity with each other, they're clustered to supernodes. So as for dimension 2, transformation of the edge set, we have the same sets of operations. Again, dimension, again, the filter and group are used to lose information, whereas add and split operations are used to reintroduce information. So applying this to examples in literature, we see that in OD maps, first of all, the edges are grouped by same pair of nodes. So recall that in dimension 1, the nodes have already been grouped by grid cell. So the next step is to group nodes that have the same grid cell to the same edges. Next, edges have been added in which there are no data available. So probably not every combination has been complete. So as for the spiral trees, the nodes also have been aggregated by same pair of nodes. So kind of a similar method here. For the mobility graphs, in the first step, nodes have been filtered by attribute value, and next to similar endpoints. So it's also basically a clustering method. So what you see is that dimension 1 and 2 are often applied simultaneously. And especially the mobility graphs, they're a nice example of that. So dimension 3. So for an individual node. So the question is, what are the ways of losing information? So an individual node is characterized by, well, its presence, of course, but also its coordinates, x, y. And we can lose this information, or partly lose it, by, for instance, a geometric deformation or by a resolution reduction. So we already saw this gridding of coordinates. However, the fundamental difference is that in the one, it's about the node set, so like the OD maps, whereas here it's about the final representation. Furthermore, there's a cost for perceiving a node. So when we consider a single black dot to be the node norm, each of the other methods have a specific cost reduction or cost increase. So for instance, a gray dot is a little bit harder to perceive, so it has an increased cost, whereas a flickering dot has a reduced cost because it's easier to see, especially when the other nodes do not flicker. If we apply this to literature, for instance the map by Minard, we see that a geometric deformation has been applied because in this case Europe is an important continent and normally it's very small, so in order to make a little bit more space. This circular plot, the coordinates have been replaced altogether by a circular coordinate. As for D4, the question is the same as for dimension 3. What are the ways of losing information? Well, for an edge, there are a little bit more core variables, namely endpoint 1, endpoint 2, the ordering of those points, the direct path, and the length. Each of these core variables have a specific cost of perceiving them, which can be increased or decreased. So we consider a straight arrow to be the edge norm, and each of the core variables are shown. When we change the way in which an edge is visualized, then we see that some of these core variables cannot be observed anymore. Others can be observed, but a little bit harder. And moreover, there are some that introduce a derived variable, for instance, middle point. When we apply this to literature, we say that in mobility graphs, dimension attenuation has been applied with respect to direct path, length, and ordering. It's harder to perceive them than via an arrow. In the world migration map by Minard, similar dimension attenuation has been applied, and furthermore a dimension enhancement. So the edges are nicely routed over here. And finally, in the circular plot, a dimension attenuation with respect to ordering has been applied, and a dimension reduction because of the circular coordinates. So this table shows a formal classification of the methods in dimension 3 and 4. More information can be found in the paper. So the design space allowed us to find a new design. So how can we approach this design? In dimension 3, we saw different ways to represent a single node. And in the latter examples, especially the circle, we thought, okay, we can replace a circle by proportional symbol, such as a donut, which can hold other information, such as the outflow. As for the edges, we saw in dimension 4 the half-lines. And in this specific application, the half-lines have a huge benefit, because normally when there's a flow from node A to node B, there is often an opposite flow from B to A. And these two half-lines, they nicely form one line, so to speak. So it works really well in this application. So in general, what are the ways to explore a design space? Well, if we look at users, data and tasks, It's of course good to know the users. Also, to know the tasks, quite obviously. Then there's the benefits of interaction. So it's often specific benefits to start with like global first and then details on demand via interaction. Also, it's worthwhile to investigate the trade-off between dimensions or trade-off between implicit and explicit encoding. Basically, a good approach is to start with a simple information reduction. So typically, OD data is very large. So as we see in all examples that we studied, I think there are 8 in the paper, all of them have aggregated the nodes and edges somehow. And finally, it's good to start with an existing design, with a similar application, similar setting, so the user's data tasks, and then try to change it if needed. So finally, information theory applied to data visualization is basically 2 sides of the same coin. So visual design is to find the best way to depict some information, and in the same way to find the best way to lose some information. Thank you for your attention.
Thank you, Martin, for that clear presentation. So we have Martin here to answer your questions. First question from Wolfgang Agner has asked whether you've looked at encoding directions of movements and also things like time and network dynamics into these graphics.
Yeah, thank you for your question. Yeah, that's a good point. So we looked at kind of different levels of abstraction, and it's really one take-home message from this research was that it really depends on the data and on the tasks. So when you look at trying to look for a certain proper design, then you want to find the best the best solution available. And so with this information theory approach, we were really kind of successful, at least in our example. Yes. So.
Okay, thank you. There's a question from Gennady about scale or multiple scales, and also from Wolfgang. So does your design space allow for depicting movements at different spatial aggregations at the same time?
Not yet. That's one topic for further research, to allow for like a hierarchical structure of movements. Of course, you can decide to aggregate some nodes and make them super nodes, add them additionally to your data set. But it would be better to have that implicit in the design space in one way or another. But it was already quite challenging to make a design space that's as general as possible with its information theoretic approach for just plain graphs. But yeah, I'm really looking forward to work on that. I'll think about it.
Okay, thank you. So in your talk, you mentioned that the data may influence what the best design decisions are, and also the task. But I think you don't, in the paper, don't very clearly give recommendations for those. So if we start with data, question from Jason Dykes. So certain configurations work better with different designs. So necklace maps work better with certain spatial configurations. OD maps work best for kind of square areas. Donut maps work better in some situations. So have you got any thoughts on what are good techniques for what data characteristics?
That's slippery ice. I mean, that's really, for instance, with the donut maps, we have applied donut maps for data sets in France, Germany, and Ivory Coast. The thing is that donut maps only work well when there's some kind of local. Then there are a lot of local flows, so people live relatively close to their work. So then it really works. But for instance, in France, we studied migration during the COVID, and then people migrated from Paris to the Alps. And then it created huge half lines. So even the half lines were kind of tall. Yeah, so donut maps work well. I also looked at Discord question. I think Jason Dykes mentioned that the large donuts cover part of the half lines. So that's kind of fun thing that we have to look into. So in that sense, the donut maps are not perfect, but yes, they're better. I think for the other techniques like OD maps, necklace maps, yes, some work better for certain spatial configurations, other for other. But however, we don't want like a taxonomy or something like that. We don't want classification. If the dataset is this, to use that. If that, because then you can always find exclusions. So
I think it'd be quite a nice exercise to map out your design space, and for different data sets and tasks with different characteristics, say which ones are likely to be most suitable and which ones are likely to be.
Yeah, if they're used as a guideline, yes, but you shouldn't hang on too much weight to it.
Sure, it should be just guidelines. Thank you. And a final question asked by a couple of people is, what came first, donut maps or the design space?
I think it's a little bit hand in hand, but the design space was for 90% finished, I would say. And then I had a sort of like an idea, and then Min said, okay, why can't we use half lines, because that's one of this dimension 4. So then, and I thought about this glyph, so it kind of moved in nicely. But yes, it's combination.
So it's sort of co-evolved then.
Co-evolved, yes, yeah. Yes.
Yeah. Okay, great. We're out of time. Thank you very much for your talk.
You're welcome. Thank you.
Okay, welcome back. Just a comment from Jason that the presenter should really have a look at the Discord chat, because there's a lot of interesting comments on there that are probably worth looking at. Okay, now we're going to move to our next paper, our third talk, which is about the visual analysis of spatio-temporal phenomenon with one-dimensional projections. And that's by Max Franke, Henry Martin, Steffen Koch, and Kuno Kurzhals, in which they give design space for collapsing two-dimensional space to one-dimensional space for spatio-temporal analysis. It will be presented by Max.
Hello and welcome to the presentation of our paper, Visual Analysis of Spatio-Temporal Phenomena with 1D Projections. My name is Max Franke, and I am presenting on behalf of my colleagues at the University of Stuttgart, the Swiss Federal Institute of Technology in Zurich, and the Institute for Advanced Research in Artificial Intelligence in Vienna. For the analysis of spatio-temporal phenomena, such as earthquakes, wildfires, or the spreading of disease, identifying spatio-temporal regions of interest on a glance is of importance. For our work, we formulated a set of tasks our approach aims to solve. These are derived in general from the movement taxonomies of Andrienko and others and Dodge and others. The first task is the identification of hotspots. Hotspots are spatial regions which, within a time frame, exhibit high values. A second task is to find patterns of synchronization. That is, geospatial entities whose time series exhibit similarities even outside of a geospatial context. Third, identifying trendsetters is crucial to understanding spatio-temporal phenomena. Trendsetters are geospatial entities that first exhibit certain time series characteristics, which then spread to its neighbors. Additionally, we want to support more general visual analysis tasks. One is the retrieval of detailed information on demand, and the second general task is to understand relations between data cases and between attributes. For representing spatio-temporal data, glyphs in a map are often used. However, glyphs are only scalable to a certain extent, both regarding their temporal aspect and their spatial aspect. Another popular representation is animation, where time is mapped to time. However, the temporal scalability or resolution is limited, and change blindness can hinder comparability between time steps. Recent work, such as motion rugs and dynamic volume lines, have explored a different approach, where space is projected to the one-dimensional domain, and time can then be mapped to the second axis. We extend that approach by interaction and visual guidance. Our conceptual data pipeline looks as follows. Input data is usually point data, or at least has a defined center. Each geospatial entity has a time series attached to it. The geospatial entities can optionally be hierarchized. This improves scalability, and in many cases, as with geopolitical entities, hierarchy is already given. Otherwise, clustering or other aggregation methods can be used. Then each subtree of the hierarchy is projected independently into the one domain. In the visualization, the children of one subtree are then visualized with the projection order on the horizontal axis and the time on the vertical axis. On selection of one element, that element and its geospatial neighborhood are shown in more detail on a separate timeline. We support a set of projections. For one, we support space-filling curves such as Hilbert or Morton curves. We have found these to be suitable, especially for projecting entities that are already laid out in a grid-like manner. Agglomerative hierarchical clustering is a bottom-up clustering approach that produces a binary tree, where deeper nested items are closer together. Traversing such a tree results in a 1D sequence, where geospatially close entities tend to be close together. We have found those projections to work well with less regularly laid out geospatial entities. With agglomerative hierarchical clustering, different linkage criteria can be used to decide which two clusters next to merge, and we support the most common variants where applicable. To support time-oriented tasks, we also offer ordering based on time series similarity using dynamic time warping. We also offer an ordering by the first time the time series crosses a certain threshold. To support decisions on which projection is suitable for the current data and task, we calculate quality metrics for the projections. The M1 and M2 scores introduced by Venner and Kasky measure the trustworthiness, that is, how few high-dimensional data points are projected into a new neighborhood, as well as the preservation of original high-dimensional neighborhoods. These metrics measure local projection quality. Because those measures are familiar to analysts, we also calculate metric and non-metric stress, which are the loss functions of metric or non-metric multidimensional scaling. However, these are global measures that do not always reflect the intended result. We normalize both metrics to the interval from 0 to 1. Our prototype consists of a map, a hierarchy icicle plot, and a projected timeline. For indicating pairwise distances, we also show a distance bar over the projected timeline, where higher distances are mapped to darker colors. When selecting a geospatial entity, either in a map or in the timeline, it and its neighbors are visualized in more detail. The point of time shown in the map can be controlled and animated. The projection selection shows quality metrics for different projections, and analysts can switch between projections here. The cutoff radius for detail neighborhoods can also be tweaked. We can drill down into subtrees of the hierarchy by zooming in the projected timeline. Here we drill down to the counties of New York State. The cutoff radius for neighborhood selection can be tweaked individually on each hierarchy level. When clicking on an entity, it is selected as a nexus and shown with its geospatial neighborhood in the detailed timeline. Alternatively, we can select a rectangular area in the timeline. This will not always produce a contiguous result, but we can restrict temporal extent on that selection for more temporal precision in the detailed timeline. To understand the effect of a projection, its path is shown in the map when hovering over the projection. We can resort the projection list based on each quality metric. Here we sort descending by the M2 metric. We can now see that the AHC Ward projection has the highest M2 score. As a reminder, a high M2 score reflects the preservation of the high-dimensional, that is the geospatial, neighborhoods in the 1D projection. It seems reasonable that Ward's linkage criterion on agglomerative hierarchical clustering performs well here. When hovering, we also get a tooltip showing the difference in ordering from the current projection to the hovered projection. We additionally offer tooltips which show the current nexus and selection in all projections. This way, analysts can see how different projections behave for a set of entities. Of course, we can also do this for a contiguous selection, where we selected a rectangle in the projected timeline. What we can see in both cases is that the selection we have stays more or less contiguous in different projections. Analysts can then compare these projections for different selections to understand which projections are suitable for what they are analyzing. Our first application scenario is the current COVID-19 pandemic, where we get day-by-day global statistics from covidatlas.com. Here we can formulate the hotspots task as: are there regions with higher number of cases? The synchronization task can be formulated as: where did case numbers develop similarly? And the transitor task can be formulated as: where did regional infection hotspots originate from? For the COVID-19 scenario, we represent case counts normalized by capita as circular colored markers. Either the total number of confirmed cases or the number of active cases can be visualized. In the detailed timeline, both measures are shown as area charts. The second scenario involves the heavy wildfire season of 2019 and 2020 in Australia. Here we have satellite imagery of thermal radiation, which we aggregate into square areas with side lengths of 1 kilometer, 10 kilometers, and 100 kilometers. Here, the hotspots task can be formulated as, are there regions with many wildfires? The synchronization task can be formulated as, where did wildfires spread or develop similarly? And the trendsetter task can be formulated as, where did wildfire regions originate from? Of course, with both application scenarios, the general tasks of retrieving details and relations stay relevant. In the prototype, we represent the aggregation areas as choropleth markers with a logarithmic color scale. We use a matrix visualization for the detailed timeline as well as for the projected timeline. To get an understanding of what patterns to expect in the projected timeline, we generated artificial spatio-temporal patterns and projected them. Here we have a graph where one node has a defined value over time. This value then spreads to adjacent nodes over time. In the projections, the spreading can be seen quite clearly, as well as the trendsetter, and we can also see the contiguity of the entities with values. A second pattern we generated is a ring of high values that spreads outwards over time on a grid. In the projection, we get these chevron-like patterns, which start at local trendsetters. What we also noticed with these grid layouted data, such as this one, is that since all neighboring cells are the same distance apart, the projections based on agglomerative hierarchical clustering are rather arbitrary in the results, and the space-filling curve-based projections are much more contiguous or logical. Let's look at an example analysis in the wildfire application scenario. We identify a spatio-temporal hotspot in the timeline, which we want to analyze in more detail. We drill down into one of its entities and zoom in a bit in the map. We then select the temporal extent of the hotspot and zoom in a little bit more in the map. And then we select the first day of the time interval using the time control slider. Here we can already see a trendsetter. You can see this trendsetter both in the map because this is the only entity that currently has a value, and we can also see it in the timelines where it is the highest peak. Now, let's zoom into this trendsetter. Let's select the temporal extent again and zoom in the map. So here we have this trendsetter again. Let's confirm in the time controls that this is actually the first day. And yeah, it is. So this is the trendsetter, or these are the trendsetters that we were looking for. And what we can do now to further analyze how this wildfire developed from here on out is to animate the following weeks and look how the wildfire will spread outwards in a ring-like fashion. Keep in mind that the satellite did not always pass over these regions each day, so we have some gaps in the dataset. But other than that, we can see very clearly how this wildfire spreads out in a ring-like fashion, which is very similar to the artificial dataset I showed you before. Feedback from visualization and domain experts stated that they saw the projected timeline with its static display of patterns as a key advantage, stating that traditional GIS-based visualizations mostly resort to animation or to temporal filtering to let the user interact with the temporal features of the data. However, we also noticed that the complexity of our prototype required some learning time, which makes it more suitable to domain experts than to casual users. We have found the projected timeline to be very helpful for identifying potential regions of interest, such as hotspots, trendsetters, or synchronization. However, the produced patterns are not always clear, and the projected timeline should therefore be used as a starting point for a more detailed interactive analysis, using traditional methods such as animation to verify and to further analyze the data around the region of interest. We found that helping analysts to understand the effect of different projections can also help with understanding the data. We do so with tooltips and visual guides. A lesson we learned during the development is that the granularity of the hierarchization matters. While hierarchy helps to scale up the supported dataset sizes, two nested hierarchies or two small subtrees hinder navigation and analysis. Our approach can be used in many domains, and for certain analyses, the temporal component could even be replaced by something else. A future improvement to the approach could be to allow for dynamic tweaking of the projections, as some of those are parameterized. Because calculating those projections is expensive, we have done so until now in pre-processing. And with this, I want to thank you all for listening. This work has been supported by the Volkswagen Foundation, the German Federal Research Foundation, Germany's Excellence Strategy EXC 2120/1, and a Mobility Initiative grant funded through the ETH Zurich Foundation. If you are interested, we have made the source code for our prototype available on GitHub. And if you just want to try out the prototype itself, we also have hosted a live version of that. And now, I will be happy to answer your questions. Thank you very much.
Okay, well, thank you, Max, for that nice presentation. And there were lots of comments about complimenting you on your very interactive system. So well done.
Thank you.
So we have Max here to answer some of our questions. So one question I have is that at the end of your talk, you kind of said that the 1D projections were a good starting point, but that animated maps may be best way to see what the patterns are. So I wondered, it's good, and it's good that you had your synthetic data sets, but are there any other spatial patterns that you found particular 1D projection techniques work best for, apart from the rings and the other one?
Well, we also looked at spots that wandered over the map, like linearly wandered. Those were also visible quite well, but we didn't find any real world data set where you could actually see those. So this was a little bit hard to justify, so to speak, the artificial data set for.
Okay. And did you find that it mattered which 1D technique was used? So users can look at them all, but all of them give you a different perspective. So what was there one that people converged on?
Well, we had some experts look at it, and what we noticed was that they really focused a lot on the Hilbert curve. And it might be just because that was the one that was initially shown, and they didn't explore enough. And as we also discussed in the paper, these space filling curves, they work very good on grid patterns, and hierarchical clustering based projections work better on irregular layouts, but the space filling curve work surprisingly well also on those data. except for some edge cases.
I do wonder though whether some of the metrics might not reflect some of the important geographic patterns such as coastlines and other features as well. But I guess you can always have a go at incorporating some of those into some of the projections later.
Yes, absolutely. So especially the global metrics, they don't really reflect what is going on in the data. And the M1 and M2 metrics, they do a good job. But of course, yeah, if you have something like coastlines or closed borders in the case of the pandemic, it might be more interesting to look at topology, and there might be more suitable metrics there.
Okay, there's a question about users. So you looked at the system with some users and you gathered some opinions. So could you talk about that? How long did they interact with the system for, and how did they use the 1D projections?
Yeah, so because of the situation, this was all done virtually. So they used it at their computers and we watched via Skype. And the sessions were typically like 1 to 1.5 hours. So it was not very long. What we saw was that the system needs quite a bit of time until you really understand how it works. So it's a bit complex. What we saw was that some used the map first and then looked at the data, and some explored different projections and first looked at the timeline and then looked at the map. So there were two different approaches to how to explore this.
Okay. And a final question is that somebody, Jules has asked whether it's important to have the same projection throughout the whole of time, or whether there are advantages in changing the projection at different time steps. Any views on that?
That's interesting. We have not thought about that at all, but the problem is that then you have to like swap the lanes in the timeline, right? Because the ordering changes. So it would look quite different. I'm not sure how well that would work. I guess you would have to try that out.
I mean, maybe you could do it if you want to detect a particular pattern. Maybe you can use that pattern to inform a change in the dimension and then see how much it deviates from that, perhaps. But
yes,
these are things that can be looked at later. Great, thank you very much. We'll move on now. So thank you for everyone's questions too. Okay, so our final talk is on boundary objects and design studies, reflections on the collaborative creation of isochrone maps. And that's by Romain Villemont, Philippe Rivière, Anel Bergon, Aurélie Tanard. And this work's interesting because it helps us think about the design process in design studies, and it perhaps helps us generalize the outputs. It will be presented by Romain and Aurélien.
Good morning, everybody. My name is Romain Villemont, and I will do this presentation with Aurélien Tabar. Our work is related to improving urban mobility. I will first introduce the motivation for this work, as well as the main results, which are those novel isochrone maps. And in the second part, Aurélien will provide a reflection on our design process. So here is the context of our work. Let's say you just arrive in Zurich at the train station and you have a couple of minutes to spare. You might ask yourself, how far can I travel? And you might think all your travel destinations are within this circle. And that's true. That's true if you're a bird. But if you're not a bird and you only want to walk and you don't want to climb a mountain or swim in the water, then your travel map, your travel opportunities are as follows. They follow the roads or the streets. And if you plan to take the bus or the metro, then your travel map will follow the metro or the bus transportation lines. So those travel maps have a name. They are called isochrone maps. They are very good to capture how far you can go within a certain amount of time. They basically show you all the reachable areas on a map from a given starting point. They also emphasize the regions with high accessibility. That means usually the regions with streets or roads or metro lines. And they also communicate the regions that are difficult to reach because either they have no public transportations or because there are some physical elements like the mountains or water. However, those maps, they have some disadvantages. They usually do not communicate why some regions are accessible or not. You don't really see the metro or the bus lines. Usually they are only designed for a given time of the day, like in the morning or in the afternoon. You cannot really get a big picture of all the travel times during the day. And they are challenging to read. Here are some examples of issues with isochrone maps. Adjacent regions are difficult to compare in terms of travel time. It's difficult to grasp travel directions. And finally, it's difficult to connect isolated areas to the main region. So our goal is to fix those issues by using geographical layers, which basically are the layers being used to create those isochrone maps. And we will see how we can use travel times, itineraries, and metro networks, which are part of those layers, to improve the design of those maps. So let's just use all the layers, which is probably the most straightforward option. But as you can see, it actually creates more issues than it solves. So instead, we will pick the right information from the right layer by following the cartographic generalization principles. Those principles have been introduced in the 60s, but Zillian in 1993 summarized them as follows. So first, those principles tell us to select information, which basically means to select some layers rather than others. So for instance, we might use the layers for the bus lines rather than the layers from the background map. It tells us to simplify the information from those layers by filtering out some elements, smoothing the layers to reduce the geometrical appearance of the shapes, add some exaggerations to emphasize some elements that are important on some layers, add some displacement to prevent visual clutter, and of course, those principles can be combined together. So this is what we're going to see in the next section of the talk, which is about the design study, where we show how user picked the right information from the right layers using those principles. But before getting there, I will present the results we obtained from this study, which is this map, a simplified isochrone map, following the cartographic generalization principles. So as you can see, this map emphasizes the transit stops and shows the directional information in the same time. It shows the underlying network, which is here the metro line from the center of the city towards the periphery. But as you can see, the metro network is not visible everywhere. So it's only visible where it's important to connect the previously disconnected areas. This map shows the isochrone steps, which enables to compare all the regions with the same accessibility for every 10 or 15 minutes. And finally, we show the base map, which is the background map that tells us where are the physical obstacles, such as rivers or elevations. This map is available online as an interactive prototype, and we've seen that it provides some interesting insights on the accessibilities of cities. So as you can see in the center of a city, usually it usually is very accessible. You can go to any directions. If you're outside the city, the accessibility is towards the center of the city. And finally, you have some inaccessible areas, that mean areas without any public transportations. We also use this tool to generate some design variations. We're going to talk in the next session of this talk.
Thank you, Romain. I'm going to take over to reflect a bit on the project. So our team was composed of 5 people anchored in different disciplines: visualization, design, geographic information system, cartography, and human-computer interaction. So the project unfolded over a year. The first phase of almost 6 months consisted mostly in surveying existing isochrone approaches and refining the problem and the project at hand. We worked on other projects involving isochrone maps in parallel. The collaborative period lasted for 4 months, with a design exploration phase that led to the definition of requirements, and this involved various tools, platforms, and collaborative documents that I will come back to in a bit. The following period consisted in more hands-on exploration of design directions, involving real location and realistic data. We conducted various workshops and frequent meetings and discussions discussing design directions. Finally, we created a parametric design tool connected to live data, which enabled us to collaborate on generating almost real-time design alternatives. With this tool, we could collect feedback from external experts with whom we collaborate. So here we are in a situation in which design studies typically will focus on such processes, unpacking design choices at various stages of the project, the expert feedback collected, the compromises, and distilling lessons learned. Yet, processes are notoriously challenging to apply to other contexts, as they heavily depend on situated constraints that vary from project to project. And so, reflecting a bit on how to improve the transferability of design studies, we suggest that reflecting on the tools, documents, and other artifacts used could be fruitful. We'll try to illustrate our point by discussing the tools and artifacts we used while collaborating, the documents we shared, the notebooks we used, the printouts and sketches that we relied on. We build upon the concept of boundary object, which has been heavily used in the science and technology studies literature and closer to us by the CSCW community. Starr and Grismer define boundary objects as objects which are both plastic enough to adapt to local needs and constraints, especially of several parties employing them, yet robust enough to maintain a common identity across sites. They are weakly structured, they say, in common use, yet become strongly structured in individual site use. The concept of boundary object was introduced to analyze the cooperative processes among multiple actors working on the creation of a zoology museum. Starr discusses how patrons, the director, amateur collectors relied on a set of collaborative objects to work together and resolve tensions. Such objects involved, for instance, in their case, specimens for the zoology museum, but also maps that were used. The most noted property of boundary objects is their interpretive flexibility. The same object, like a map, can be understood and used differently by different groups of people depending on their expertise. Such boundary objects facilitate collaboration by supporting negotiation within multidisciplinary projects. And so in the rest of the presentation, I'm going to discuss 5 different types of boundary objects that we encountered in our collaboration. The first one is a structured collection. We created several collections of maps, like Isochrone maps collections and mood boards. This relates to Starr definition of repositories, which are a specific type of boundary objects. Repositories are collections of objects or piles, as used by Starr, that are indexed in a standardized way. So by indexing and standardizing, repositories help manage problems of different lenses or units of analysis across disciplines. In our case, the survey helped us to identify and discuss isochrone properties. It also had limits, so like any repository, we left out some elements that were difficult to characterize. So for instance, in our case, the visual signatures of isochrones, the kind of branches or dendrites, the organicity of the shapes, were very difficult to encode, and we left them out, although it could have been interesting. But overall, structured collection helped us to frame what should be considered an isochrone and align everybody on the project and define the kind of degrees of freedoms for prototyping later and put names on the things we would work on. Our second category or type of boundary objects are structuring artifacts. Here, our main structuring artifact was a requirement list, which guided our initial exploration and helped us to negotiate a common direction. We also created various maps, especially our designer colleague, that served as really kind of design directions and development direction for the cartographer and the GIS expert. These structuring artifacts had two properties. First, they were really pivotal in the project. They enable us to set design parameters and narrow the design space to go in one specific direction. And secondly, we came back to them often at different instances in the project to check whether we're following our initial design sources and discuss if we're going in the right direction and the one we initially set to. Our third type of boundary objects that we encountered were process-centric artifacts. These are documents that enlist group participation and capture created knowledge. In our case, we had two main types of objects, meeting and stand-up notes that we kept up collaboratively at a very frequent pace in an online shared document, capturing progress, to-dos, blocking problems, and a process book that was more describing the type of visual outcomes that we're producing. We also worked with more generative artifacts. These are typically paper maps or computational notebooks towards the end of the project. These generative artifacts are dynamic. They can be manipulated, shared, and remixed. They didn't directly serve as specifications, and we did not use them to define a specific prototype. But we used them. They were not using realistic data, coherent data, or even the right transit network for the right shape of Isochrone. But that enabled us to explore in a very dynamic way, remix and share ideas that we had about the design. Finally, some artifacts help us connect together at a higher level. While some of the artifacts presented here were co-created by the team, these bridging artifacts were produced, as whether it was paper or code, by one team member who then presented his or her work as a manifestation of the prototype, either through screenshots or a link to a notebook, for instance. In any case, these artifacts were directed from one person to the rest of the team, expecting feedback, but no direct involvement in the prototype development. As the development progressed, our design and cartographer colleagues integrated various iterated upon design choices, fixed technical problems, and this process was often conversational. And this bridging artifact helped us to basically enable this conversation. Interestingly, what we can note here is that the status of an artifact can change. Whereas our observable HQ notebook was more of a bridging artifact towards the end, once it was developed and could be appropriated by the whole team, it changed its status to become generative, whereas at the beginning it was more of a bridging artifact. To conclude, we presented novel Isochrone map designs and a parametric design tool to generate alternative designs. We further propose to leverage boundary objects in design studies and suggest 5 types we identified. We think that reflecting on collaborative tools and documents could further foster transferability of design studies. Looking at types of boundary object can help us see through the specific of projects and generalize to other contexts. As perspectives, while looking at the boundary objects involved in our design, we noticed that some types were better supported than others, meaning that they were easier to manage or capture. This opens up opportunities for the development of collaborative tools that support visualization design processes. On a positive note, the creation of structured collection was well supported, and we use an online spreadsheet and exhibit, but other tools such as surveys are already available to the community. Managing framing artifacts was straightforward, since their quantity was very limited. One question is whether we could have improved them by applying more structure to them. We captured generative artifacts mostly through screenshots and photos. This was actually quite limiting, especially for animation effects, which were really difficult to convey and capture. Another challenge we encountered was collaborating around these artifacts remotely. We need better collaboration tools for visualization. Process-centric artifacts were the least supported. Different threads of design explorations were explored in parallel, creating a classical tension between a chronological structure and a thematic one on the design side. On the code side, it was much more challenging to capture and share progress. In both situations, commenting on the content of the process-centric artifact was challenging. For example, the shared document only supported comments on an image level, and in notebooks such as Jupyter or Observable, the commenting system is quite limited. Finally, although code can be versioned, in practice most of the intermediary prototypes are not accessible anymore, which means that we cannot easily reproduce intermediary results that we could find interesting in retrospect. Finally, bridging artifacts were mostly used informally to support discussions. Under such conditions, they were not recaptured, which means that some of the design rationale got lost in the process.
Okay, thank you very much for that interesting talk. I'm joined with the two masked presenters. My first question is, if you don't mind me saying, the case study was quite a straightforward and simple one, whereas many design studies can be quite complex with lots of multiple coordinated components and diverse users. So I wonder if you've thought about whether this way of thinking of generalizing design studies could apply to a more complex design study where there may be more dependencies between the visualization designs that are produced.
Yeah, so thanks a lot for the question. So it's a great question, and I think it relates back to where we are drawing this from. And actually in the science and technology literature and that type of studies typically started with much more complex research programs or kind of work on much more complex artifacts, like, I don't know, some space mission or like complex e-science projects. And the notion of boundary projects is really related and was used in this kind of very complex with multiple stakeholders. And so we took it and used it for a much simpler thing that was easier to, in a way, to explain, but it could definitely work for much more complex project. And that's the interest, is that then you can really focus on the objects that are shared by the multiple stakeholders rather than trying to explain all the relationships that are there. And sometimes when you have tens or hundreds of people, it becomes super messy and you cannot describe all the interactions between all the groups, the different actors. But focusing on this kind of shared visualizations, maps, and other objects makes it a bit easier to have an object of inquiry and an object of study in a way. So we don't have that experience, but based on the literature, we can say that hopefully that's where what we should go toward.
Okay, so I understand that the study was relatively straightforward, so it was easy to link it into your framework. But yeah, in your paper, you've got the timeline of how the various people interacted, and it's quite linear. So I was wondering, how that would adapt if you had a project with multiple dependencies.
That's another great question. So there is always a question of narrative, and I guess here we also try to simplify the way we're telling the story for clarity. There were clearly some kind of feedback loops, and we came back to, for instance, to some of the early sketches. We came back to them very often, and they served as kind of anchor points, and we point to them at one point in the timeline, although they were used at several later stages, for instance, and we came back to that. We do not really represent it in the timeline of the project. We mention it a bit in the article itself, but clearly there should be branches and arrows and that kind of thing. We tried to make it yeah, somewhat legible. I think that was one of the remarks from the review from the previous timeline we had actually in the in the first version we submitted, and we kind of streamlined the presentation.
Okay. And as a question from Jason Dykes, apparently there was quite a lot of chat on Discord about what we learned from this. So what did you learn in this case study about the design choices alternatives, and how, for example, how quickly the various stakeholders converged on a design?
Okay. So what we can learn from this. So our main message was really that basically to also pay attention to this, and not only to the process or the various stages that we just mentioned. And then I think that's something from reading a lot of design studies. It's something that we find is somewhat missing from many discussions, where these kind of intermediary artifacts are actually useful for collaboration, but that knowledge is not really shared in articles. And basically coming back to these things that facilitate collaboration and certain types of collaboration, so it can be more to make sure that everybody agrees at a given stage of the project, or that it helps to generate a lot of ideas, or actually to pick one among many. And basically there are different types of sketches, of prototypes, of probes, or various technical artifacts that you're going to leverage. And our idea was to start to describe this, and it's I think a project that should go through many different other analysis for that kind of thing. But really the idea is to pay more attention to these, so that basically we also share this knowledge within the community. And at this stage, clearly we only based the paper on one case study, so it's difficult to generalize.
Okay.
And but our point is that we would love to have this in more case studies, as in more design studies, so that based on a larger corpus of projects, we can actually start to discuss how we're using documentation tools, how we're using sketches, because right now it's a bit hidden in the papers. And that's the type of thing that we normally discuss during conferences or around within projects, but that don't really show in papers.
I think it's good advice to keep track of the intermediate artifacts, because they are quite important. Final question from Wolfgang Agner is, what's the relationship between generative artifacts and data sketches? Is the latter a subset of the former, for example?
That's a good question. I'm not sure I have the answer. I don't know if you have one. So we actually, so maybe to come back to the writing of the paper, we discussed quite a bit what should be the names of the categories, and we are not like extremely confident. And I think these names are still open to discussion in some ways. I think there is with sketching, there is clearly this aspect of being generative as well. So it could be that the two are quite overlapping, but I don't have a more definitive answer on this at the moment.
Okay, thank you. We're out of time. It's a question from Till Nagel that maybe we can follow up on Discord.
Yeah. Thanks a lot.
Thank you very much for attending the session. Thank you for your questions. There were some useful papers, a useful discussion. Have a good afternoon.